Good evening students, myself Shomrat Paul. I am going to present a topic on pulse width modulation or PWM. Actually, the PWM is several types. It can be single pulse width modulation, multiple pulse width modulation, sinusoidal pulse width modulation, modified sinusoidal pulse width modulation, and phase displacement control. So in which first we are going to discuss about the single pulse width modulation. Okay, and in single pulse width modulation control, where means there is only one pulse per cycle has been generated and the width of the pulse is varied by controlling by two signal. One can be called carrier signal and different one will be reference signal. And in this phenomena we are going to implement the appropriate gate pulse to the gate. Means what? Actually we know the simple inverter circuit which is constructed in this way. Here the switch is there, okay, here the another switch is there, load is connected over here, and the another switch is here and the other switch is here. And we know the name of the all switches, that there is Vs, okay, that is suppose S1, that is suppose S2, that is suppose S3, and it is S4. That means when we are going to switch on the in case of inverter circuit, suppose S1 and S2 should be on, and then S3 and S4 should be on, right? So if we consider S1 and S2 is on, that means at the first case we should focus to give the appropriate switching pulse to the S1. That should be again will be reflected for the S2 at the same instant. Similarly, in case of S3 and in case of S4, again we will get the same triggering pulse across any instant. But never we can apply the triggering pulse across the switch S1 and S4 at any instant. Then it will provide a short circuit path. Then the S1 and S4 will be damaged permanently due to huge amount of current starts flowing across the switches. That is why always we are trying to give the appropriate switching pulse across S1 and S4 where they will not provide any short circuit path. Okay, that is why all the cases we are going to give the appropriate triggering pulse across the switches. That is why all the cases we are going to explain further by using gate pulse across G1 and G4, and always try to maintain G1 and G4. The output, the gate pulse will not be same at the same instant to avoid the short circuit path. Here we are going to explain the single pulse width modulation. It is actually applicable for the voltage control purpose for the inverter. Okay, so that means what? When the switch a G1 means the switch S1, S2 and S3, S4 starts conducting as the inverter operation, we know it will provide the positive pulse in the first cycle and it will provide some negative pulse. That is why it will generate the periodic signal in this way. This is the inverter operation. That means we can say this inverter operation is actually depends on the appropriate gate pulse. That is why this voltage is defined by Vs into G1 minus G4. That means this is the gate pulse. How it can generate, just I will explain later, but right now try to understand this is the gate pulse which has generated. That is not the output voltage of inverter. This is the gate pulse means this pulse that should be given across the gate of the appropriate switch. When the gate pulse is given, then switch starts conducting, then the voltage is appearing across the output voltage. When it stops giving the gate pulse to the switches, then the no voltage is appearing across the output voltage. Okay, that output terminal. That is why we are focused to maintain the appropriate gate pulse. That means by PWM technique is actually used to provide the appropriate gate pulse for the respective switches. This is the main thing I want to share you. Okay, and in the first case, see, as it is a single pulse width modulation, that is why, and the gate pulse that has to be generated by comparing the signals. Here we are using rectangular shaped reference signal and the triangular shaped carrier signals. So this is the triangular shaped carrier signal having the amplitude of AC, and this is rectangular shaped reference signal having the magnitude of AR. Okay, and this is the point where the both signals are coincides, through which we can determine the width of the pulse. That is why this is called pulse width modulation or PWM technique. That means we are changing the width of the pulse as well as the amplitude of the pulse. That means we can change the triggering pulse to the gate. So respectively, obviously the output voltage of the inverter will change. That is why we can change or control the inverter output voltage by giving appropriate gate pulse to the respective switches. That is why this is called voltage control technique using single phase pulse width modulation. Okay, now see, so first, suppose for an example, here we are using the reference signal, this one, and the carrier signal is this one, and both signals are coincide at this particular 2 points. So to further extension, it will give this region, and this is the width of the pulse which has to be give to the switch S1, and this pulse width we are assuming this is suppose defined by delta. So that means this part will be delta by 2, again this part will be delta by 2. That means this point should be, that is pi by 2 minus delta by 2, and it will be pi by 2 plus delta by 2. So this is all about for the gate pulse across switch S1. Now across the switch S2, okay, as we know, these two switches will not be short circuited. That is why we are not applying any gate pulse during this region. Okay, so we will provide the gate pulse for the next cycle, means 0 to 2 pi. Then we are applying the gate pulse across G2. Similarly, from this point and this point, which will the further extension, which will provide you this kind of shape across the gate pulse of switch G4. Okay, so from these two waveform, that means we are applying the gate pulse for the first half cycle, that is G1, and we are applying the gate pulse for the next half cycle G1 as the inverter operation. That is why Vs into G1 minus G4, which will give you the output voltage. So this is the output voltage for the positive half cycle, and this is the output voltage for the negative half cycle. And similarly, where the gate pulse we have implemented the confined region of the each peaks, that is defined by the same angle. That means it will started from pi by 2 minus delta by 2, and it will be pi by 2 plus delta by 2. So this is all about for the single pulse width modulation. As for each half cycle it provides one number of pulse, that is why this is called single pulse width modulation. Okay, one more thing, see, in this particular case, assume the ratio of the ratio of AR to AC, means AR to AC, this is wellly defined by M, that is equal to AR that is equal to AR by AC, okay, which is called modulating index. Okay, that means we are increasing this rectangular shaped reference signal from this one to upward direction or downward direction, then the coincide point will be changed, like, so similarly to correspondingly the width of the gate pulse will be changed, as well as the output voltage will be changed. That means this reference signal can be maximum varied from 0, means maximum varied from 0 to this point, the same amplitude of the carrier signal or AC. If AR can be varied from 0 to AC, then the width of the output voltage of the inverter, which will start from maybe this part to this part. That means why we can easily control the width of the output voltage of any kind of inverter by using appropriate gate pulse and using the pulse width modulation technique. Okay, so this is all about the pulse width modulation part. Now we can say in single pulse width modulation there is only one phase per half cycle and the width of the pulse is varied to control the inverter output voltage. Okay, the gating signals are generated by comparing a rectangular reference signal of amplitude AR with a triangular carrier signal of amplitude AC. The instantaneous output voltage, that is defined by VO, equal to Vs into G1 minus G4. The ratio of the amplitude, that is AR to AC, which is called a modulation index, just I told you before, that is defined by M equal to AR by AC. Okay, now easily we can calculate the output voltage, that is VRMS, that is root mean square of the output voltage, and as when the switches were on, then the immediately output voltage is reflected just to input voltage. That is why that is defined by the VS square. That means the VRMS, that is defined by 2 by 2 pi. Okay, that means in a complete cycle, number of forward peak, number of positive peak, and number of negative peak is 2, right? And just go through the waveform again. See, in case of this part, output voltage RMS value calculation, that means in the complete cycle 0 to 2 pi, there is a number of peaks is 2. This is a positive peak 1 and this is a negative peak 2. That means 2 number of peaks, and this peaks is confined between the confined region, that is pi by 2 minus delta by 2 to pi by 2 plus delta by 2. So we can easily calculate the RMS value as it is a periodic signal in this way. Okay, that means we can calculate the RMS value, that is 2 by 2 pi integration of pi by 2 minus delta by 2 to pi by 2 plus delta by 2 Vs square d omega t. So ultimately we will get the result, that is this one, 2 by 2 pi integration of integration of pi to delta by 2, that is pi plus delta by 2 Vs square d omega t. Okay. Okay. The next part is, which is reflected on the next sheet, that is here. So after simplification, the RMS value, which is defined by this one, right? That means Vs square, that means Vs square by pi omega t, lower limit pi by 2 minus delta by 2 to pi by 2 plus delta by 2, it's upper limit, that is under root. So after simplification we will get this result, and finally we will get the result, that is this one, that is Vs square by pi into delta whole, that is under root. So RMS value of this one, this is defined by this expression. Okay, now what I told you before, that means in this particular RMS value we can say by varying AR, that is from 0 to AC, the pulse width Okay, delta can be modified from 0 degree to 180 degree, and the RMS output voltage VRMS which is varied from 0 to Vs. So automatically we can control the output voltage, means we can regulate the output voltage by using PWM technique, just changing the amplitude of the reference signal. Okay, now as the output voltage of the inverter which provides the periodic signal, so that is why the instantaneous output voltage which can obtained by using the Fourier series. Okay, so V0t equal to summation of n equal to 135 as the symmetrical waveform there, and half wave symmetric, that is why 135 to infinity means odd harmonics are there. We are not taking the even harmonics. That is why, as it is a full bridge inverter, that is why 4 Vs by n pi sine n pi by g. Normally, in the first case for the full bridge inverter, this term was written by sine n pi by 2, right? And see, just try to recall, on that particular case, that suppose the waveform is just similar to this one, where this part was suppose pi and this is suppose 2 pi. That means we have taken the midpoint to calculate the periodic function, that is pi by 2. In this case, the width of the pulse that is determined by, in this case, the width of the pulse is determined by this one, right? And which is having the width, that is delta. So midpoint is this one. That is why we should taking care of the having the value is, that is in delta by 2. Okay, this is a small change that is given over here. So you can directly write the expression, and by considering the width of the pulse, that means in this particular case, all the cases, the width, this term is a sine term will be, that is sine n width of the pulse by 2, that is delta by 2. If the width is defined in by the alpha, then we can rewrite the expression suppose alpha by 2. If it has some numerical value, suppose delta equal to 60 degree, then sine n 30 degree, the expression will be formed like this. So this is all about for the single pulse width modulation to generate appropriate gating pulse to the switches.